Hi everyone, we're going to start Module 7 today, and we're going to focus on systems of equations. And the first few sections of Module 7 are going to be about how to solve systems. So we're going to start today by talking about how to graph a system of equations, and then how to use that to get the solution. But first of all, let's just talk about what a system of equations is. Now when we say system, what we mean is a group of equations. So we're going to have two or more equations, and we're going to group them together and call it a system of equations. Now what we're going to do for now, to keep it simple, we're going to focus on a nice easy system of equations where we have only two equations, and they're both linear equations only. Now as you move into higher levels of math, you're going to start seeing bigger systems of equations. Maybe they have 3 or 4 or 5 equations. You're going to see more complicated equations in there. Maybe you have exponents or radicals, things like that, but not yet. So when we talk about solving a system, what we mean is to find one answer, which is going to be a point. It's going to have an x value and a y value, and that answer is going to be a solution to every single equation in the system. Now remember, for us today, that's just 2. So what we're looking for is we're looking for the combination of x and y that is an answer to both equations in the system. So, as we mentioned in the title of the notes today, we're going to use graphing to solve the system. And what we're going to do, we're going to take the two equations from our system, the two lines, we're going to graph them, and the point where they cross is the answer. So let's go ahead and just jump in and try one out. We have two equations here. We have y equals negative 1/3 x minus 1, and we have 2x minus 3y equals 12. Our goal is to find that x and the y, where if you plug them into both equations, it works. And we're going to try and do that by graphing. So for the first line, what we have is slope-intercept form, which means this number right here, this negative 1, is the y-intercept, which would be here. And this number out here, the negative 1/3, is the slope. So if the slope is negative 1/3 and I use rise over run, we'll do down for rise since it's a negative number. So down 1, right 3 would put a point here. And then I have the line going through those 2 points. So and sometimes it's hard on my projector or on my screen for me to draw a straight line. I'll do the best I can. And now let's graph the second line. Now for the second line, remember we're using intercepts because this is standard form. The easiest way to do it is intercepts. We're going to set each variable equal to 0, which what I sometimes call the cover-up trick. Like for example, let's say we do y equals 0 first, which is how we would find the x-intercept. If y equaled 0, that whole negative 3y would disappear, and you would just get 2x equals 12. And then you divide by 2, and you get x equals 6. So the x-intercept is positive 6. That's 1, 2, 3, 4, 5, 6 to the right. And then we'll do the same thing for the y-intercept. Remember, we're using the bottom equation here. Now for the y-intercept, you say, okay, well, let's say x is 0, or basically you just cover up that 2x, and you get negative 3y equals 12. And for this one, you would divide both sides by negative 3, and y would end up equaling negative 4. So the y-intercept is negative 4. 1, 2, 3, 4 down would be right here. And if I draw in that line, the answer to my question is where those two lines cross. And I think it actually ends up being the point that I found when I did the slope of the first line. I think the answer to this question right here is that point there, which would be positive 3, negative 2. Now remember, if you want to check your answer, it should work in both of them. So let's plug in the x and the y and see if it works. So let me take that top equation. If I plug in negative 2 for y equals negative 1/3 times, and then it would be 3 for x, and then you'd have the minus 1. So I recopied the top equation. I put a negative 2 in for y and a 3 in for x. Right here, negative 1/3 times 3 is negative 1, because those are reciprocals, or you could think of it as the 3's cancel and just leave -1. So you get -2 equals, and then -1 minus 1 more is -2. So it worked in the top equation, that's good. Let's make sure it works in the bottom one. So let's do the same thing. Plug in 3 for x and -2 for y in the bottom equation. That would give me 2 times 3 for x minus 3 times -2 for y equals 12. 2 times 3 is 6. And then you have a -3 times a -2 turns into a +6. And yeah, 12, 6 plus 6 equals 12. So by plugging in, we use the graph to say, yeah, it looks like they cross at this point 3, -2. But to check your answer, you can plug it in and see if it worked in both equations. And that's how we know that, yes, this is the answer to my question. That's the one point that works in both equations. And we know that because it's the only point that's on both lines. Remember, each equation represents one line. The only point that is on both lines is right where they cross. Okay, so let's talk about some special cases and add some vocabulary with that. A couple modules ago, we talked about parallel lines, lines that run right next to each other and never cross, or they have the same slope. Those never cross, and therefore there is no answer to this question. There is no one point that is a solution to both of them. So what we usually say is no solutions. If you're graphing the lines and you notice they're parallel and they never cross, you say no solutions. And the technical mathematical name for that is an inconsistent system. Now, sometimes when you graph the line, you notice they are actually the exact same line. Maybe like one is in standard form and one is in slope-intercept form, so you don't notice it. But you graph one line, and then you graph the second one, and you notice it's right on top of it. It's the same one. And if that's the case, what we usually say is infinitely many solutions. It means that every single point on those lines is a solution to both of them. You can't give an answer because there's an infinite number of answers to every point on that line. The mathematical name for that is dependent. And then if you go back to our first vocab word, we said, we have kind of an opposite of our two words. We have inconsistent means no solutions. Well, one solution, like just a normal system where they cross, we call that a consistent solution. And I actually didn't type it into the notes, but the opposite of dependent is independent. And that would just be anything besides dependent, anything besides the infinitely many solutions. So let's do one more example here. Same type of question, we're going to try and solve by graphing. And I gave you the same set. One equation is in slope-intercept form, and one is in standard form. So let's try this out and see how it works. Start with the slope-intercept form. Y equals 2x plus 5. That makes my y-intercept positive 5. 1, 2, 3, 4, 5 right here. And then the slope is positive 2. Now remember, when the slope is 2, or any whole number, you put it over 1 to do rise over run. So from that point, it's going to be up 2 and over 1, and the line is going to look like this. Okay, first line is done. Second one, I'm going to do intercept tricks again, cover-up trick. So let's say y is 0. That leaves me with 6x equals -15. Divide both sides by 6. That doesn't go evenly. Well, it's going to be a negative because it's negative divided by positive. It doesn't go evenly, but I can reduce by 3 and get 5 over 2, or basically it's -2.5. Now that is going to be right here, which actually may have been on my line. I think that is on my line. Remember, it's kind of hard for me to draw perfectly straight lines on my projector or on my screen, but I think that one does end up being on our line. Let's try the y-intercept and see what happens. The y-intercept is when x equals 0. So if I cover up that 6x, I get -3y equals -15. divide both sides by -3, and negative divided by negative is positive. 15 divided by 3 is 5. We actually do get those same 2 points. So even though I missed a little bit when I drew my first line, I think this is one of those questions where we would say there are infinitely many solutions. Even though they're in different forms, these are actually two versions of the same line. Oops. Infinitely many solutions. We're saying, we can't really give an answer to it because there are too many of them. All the points, like this point here is a solution, the two intercepts that I circled a solution, any point on the line, here, all of these points on the line are all solutions. So we get this, I call them special cases. If the two lines are parallel right next to each other, there's no solutions. If the two lines are on top of each other, there are infinitely many solutions. They're right on top of each other, and every point on the line is a solution to both.